Hello, dear student. How are you? I am fine. I hope you will be fine. Thank you. Okay, today is the lecture number 7 of crystal field theory. The topic in crystal field theory is mean pairing energy. What do you mean by mean pairing energy? What is the mean of mean pairing energy? Mean pairing energy is represented by capital P. Yeah, that's right. Okay. How can you define what is the mean pairing energy? Actually, the mean pairing energy is the energy for electrons that if one electron is present in any orbital, indegenerate orbital, if if the other electron can if the other electron can pair up, if mean pairing energy is the energy that is required to pair up that electron in this orbital, but against the electron repulsion. This electron will uh, this electron will show repulsion to this electron, so this electron want to get some energy. After that, that can that can pair the orbital. So the energy that required to pair two electrons against electron repulsion in the same orbital, this energy is called mean pairing energy. What is mean pairing energy? Mean pairing energy is the energy which is required to pair two electrons, which is required to pair two electron against electron repulsion, against electron repulsion in the same orbit. That is called P. That is called mean pairing energy. Is it clear? Okay, let now I'm writing definition. So thank you. Okay, how can you define the mean pairing energy? Mean pairing energy is the energy, or you can say that mean pairing energy is the energy which is required to pair to pair two electrons to pair two electrons against against electronic repulsion, electron electron electronic repulsion, electronic repulsion in the same orbital, in the same orbital is called mean pairing energy. Is it clear? Mean pairing energy can be defined as the energy required of to pair two electrons against electronic repulsion, and the same orbital is called mean pairing energy. Two electrons that can pair up against electron repulsion, this the energy that required to pair these two electrons against electron repulsion. It means that one electron will show a repulsion, will show a resistance to the other electron. So the energy that required to the other electron that can minimize the resistance, that can bound the resistance, that can neutralize the resistance, that energy is called, and then paired, this energy is called mean pairing energy. So is it clear? Okay, mean pairing energy, P is the energy, P is the P is the energy for for one electron one electron pair. And also p is the energy, so p can be expressed in the unit of energy. P can be expressed in centimeter inverse. Centimeter inverse is the unit of energy. If the energy is if the electron is taken in wave, if the electron is taken in wave, so it have the energy will have the unit of centimeter inverse. And also pairing energy pairing energy depends upon depends upon the principal quantum number that is n. Also Pairing energy depend upon the principal quantum number. Pairing energy is depend upon the principal quantum number, because more the principal quantum number, more the principal quantum number will show less the mean pairing energy. Why? Because because higher the higher the principal quantum number, higher the principal quantum number, higher will be lower will be lower will be uh, mean pairing energy. But what is the reason behind this? The reason is that that the high the energy, like this is for like 3D 3D, for 4D, for 5D, for 6D. With increasing the number of shell, with increasing principal quantum number, the size of the orbital also increases. So like let assume that the size also increases. Like in 3D the size, let's suppose the size is like that, but in 4D it is away from nucleus, it is very large size, like that. That is the first, that is nucleus, that is first shell, that is second shell, that is third shell, and fourth, so on. So the fourth shell, that is first shell, that is K shell, L shell, M shell, N shell. So the N shell has very greater area, while the M shell has less area as compared to the N. So that's why with increasing number of shell, increase the size of orbital. So let's suppose 3D has size that, but 4D will be more than the 3D size, so it will be like that. But 5D, let's suppose it will be like that, but 6D should be like that. But so now we have, when with the increasing the size, it will be easy to it will be easy to pair two electrons against electronic repulsion. So the energy, the mean pairing energy will be required less, while in case of 3D the mean pairing energy will be required more. Is it clear? I hope that point will be cleared. Okay, thank you. So let's, you can rewind the video to make screenshot or to get the lecture correctly of the previous lecture. So here, now to start, we proceed forwarding. So calculation, how to calculation of total mean pairing energy, total mean pairing energy. Calculation of total mean pairing energy of dx system, or dx ion, the ion that have the centroid ion that have the number of electron and d shell. So what will be the calculation for mean pairing energy to that system? Is it clear? Okay. So let's suppose if there is m is the total number of paired electron, if m is the total number of paired electron, if m is the if m is the total number of if m is the total number of paired electrons in T2G and EG set, T2G and EG orbitals, and dx ion, where x is equal to, where x is from 1 to 10, means there will be in this system, there will there may be one electron, maybe two electron, maybe three electron. For the electron of maybe 10 electron, for that electron you can calculate the mean pairing energy for the system according to this rule. If m is the total number of paired electron in T2G and EG orbital in dx ion, and P as the pairing energy for one electron. Then if m is the total number of paired electron in T2G and EG orbital in dx ion, and P is the pairing energy for one electron, and then you can calculate that the total energy will be the total pairing energy, the total energy of pairing energy for m electron, for m is total number of electron, will be equal to mp centimeter inverse. Is it clear? If if m is the total number of paired electron, if m is the number of electron, like that is the one system, That is the system, that is Eg orbital, that is T2g, that is T2g orbital, that is Eg orbital. Let's suppose here is one electron, one electron, one electron, one electron. Let's suppose here is only one electron. So here, if m is the total number of paired electron in T2g and Eg orbital, then what will be the p electron? So here is m is equal to 1 because here is only one paired electron. One pair of electron is present in T2g sets, and there is no electron in Eg set or other electron pair in T2g sets present. So we can write that here is only one electron pair present. So we can say that the total energy for that system will be m multiplied by p, while p is the energy of while p is the pairing energy for one electron, like for that electron, for that electron, for that electron, for that electron, you can calculate that. So if m is equal to 1, so 1 multiplied by p is equal to, if p has value, p, I already told you that p has some value that called the p has units that called centimeter inverse. If there is the sum wavelength of the energy that required to pairing the energy, that require to pairing the electron against electron repulsion, that energy will be called mean pairing energy. If this energy is multiplied, if this energy is if the product of this energy and the number of paired electrons, uh, that system will call the product will call the total energy for the system. Is that right? It will be mp centimeter inverse. Yeah, it will be mp centimeter inverse, right? Okay, thank you. Let's take some example on this topic. Okay, you can take screenshot from this topic. Is it clear? So let's take come to this example. Example, calculate example calculate the total pairing energy for chromium. For chromium, it was taken 6 plus 2 ion in high spin and low spin state if mean pairing energy is equal to 23,500. So let's take chromium. We know that chromium has here. How can we solve this example? Calculate the total pairing energy. So how can we calculate the total pairing energy? Here chromium, we know that chromium has electron number. The oxidation state of chromium is plus 2 plus 2. So the electron in this case will be d4. Here is d4 electron system. So a card when we consider that when we consider that this complex is low spin complex, low spin complex, if the complex is low spin complex, then what will happen? In low spin complex, we know that in low spin complex the electron will first paired up, it is against a Hond rules. So it will be like T2G, it will have 4 electron while Eg have 0 electron. So Eg can first cannot be there polynomial, but T2 and T2G, one electron will be paired. One means it means that m is equal to 1 because one electron will be paired, one electron pair will be present, but in Eg there is no electron pair. So we can say that for T2G set that the total pairing energy will be, the total pairing energy will be equal to, pairing energy for low spin will be equal to mp centimeter inverse, where m is equal to 1, while multiplied by p, where p is equal to mean pairing energy, p is equal to 23,500 centimeter inverse. So the total pairing energy is 23,500 centimeter inverse. That is for low spin. What will be for high spin? What will be for high spin? For high spin, here is a T2G for high spin. In high spin, we know that in high spin complex, in high spin complex, in high spin complex, the electron, when high spin complex are used, when that is high spin complex. So in high spin complex, I already studied you in previous lectures, in previous class. I studied you, I teach you that, I already told you that the in high spin complex there is weak ligand used. If there is weak ligand used, then what will happen? If there is weak ligand used, so the weak ligand cannot interact effectively to the system, to the D system. So the D system will cannot be the del not the crystal field splitting will not be occur too much. The splitting will be not enough. So if it is not more, but in low spin complex it is very greater, it is very greater the crystal field splitting. So in high spin complex the ligand is weaker, so crystal field splitting is not enough large. So that's why the electron cannot be paired, the electron first electron cannot be paired, but it can be but the electronic pair will be follow the Hund rule. According to Hund rule, first pair the T2G set, after that it will be paired the EG sets. So when this system is applied to the given system, to the given numerical, chromium has chromium plus 2 has D4 system. When D4 system, so first electron will be goes into, first three electron will go into T2G and one electron will go into EG. So that's why here will no be M electron, no will be mean pairing, no will be pairing electron system, no will be paired electron. So M will be 0, M will be 0. If M will 0, we can calculate for low spin for high spin complex, we can calculate for high spin complex, for high spin complex, for high spin complex where M is equal to 0. So that total pairing energy, total pairing energy is equal to mp centimeter inverse, mp centimeter inverse, where m is equal to 0 and p is equal to 23 multiplied by 23,500 centimeter inverse, while the whole term will be 0 because 0 is multiplied. So here the total mean pairing energy will be 0 centimeter inverse. Here is no mean pairing, no total mean pairing energy required. Is it clear? So now you can also calculate any numerical value. You can also calculate the total pairing energy for the system, like that I calculate, that I explain the numerical. You can take screenshot from this numerical. So I think today lecture will be cleared. There will be no confusion remain. Okay, thank you, best of luck. Please help me to support me. There is my new channel. I started since yesterday, so please help me to subscribe my channel, to support me. It make me feel, it make me feel happy that you support me, that my students are supporting me. So please kindly support me, kindly subscribe my channel and share it with your friends. Please, thank you very much. Okay, best of luck. Be steady, be reading books, different books, different chemistry books. Thank you very much. Best of luck. Goodbye.